Hello everyone, thanks for joining us today. This video is part of a mini-series on mycelium mediating plant electrophysiological communication, or put simply, plants communicating with one another electrically by means of a conductive mycelial pathway. This video specifically regards the testing of the experimental setup. We're grateful you're here and we want to thank you for being patient with us while we get everything set up. In the last video, you saw how the setup was constructed. If you missed it, you can click the link in the top right corner of this video to take you to that segment now. These experiments will require some equipment so that we can measure the plant's responses, record them in real time, and display them in a data logging software. The glass electrode was filled with 0.3 molar potassium chloride and inserted 1 to 2 millimeters deep into the stem of the plants using a micromanipulator under a dissecting microscope. The tips of the glass electrode are broken to between 10 and 20 micrometers in diameter. A ground wire is also placed firmly into the soil alongside the electrode, acting as a reference site. An electric signal spike was observed when there was a temporary voltage difference between the electrode in the stem and the ground wire in the soil. This response was then amplified using an amplifier and fed to a computer via an AD converter. The events were observed and analyzed with a software called LabChart 7. Finally, all of these tests were conducted within a grounded Faraday cage. A protocol for testing each setup is as follows. We denote the plant we are recording in with the title same, and the plant we are not recording in is denoted with the title opposite. Once we have established the electrode and ground are properly recording, with minimal noise and with no large anomalous spikes, we zero the voltage display. We perform the testing protocol as follows to control for any artifacts in the data. We first nudge a leaf on the plant we are measuring in to see if slight vibrations in the plant will give us a response. If we get a small signal or artifact as a result of the plant moving, we attempt to better fix it in position to keep it still.
Let me get this on recording. Touch the leaf and make it bend. I don't see anything happening on the screen.
We then do another leaf nudge to see if we still get a signal. If we do not, good. If we do still see a signal, we will try to further fix the plant in position so that we can limit these vibrations. This helps control for signals produced from slightly shaking the plants during snipping.
There's touch the leaf. Well, little, not a fast artifact, it's just like before, but I mean like the soil, but not as much. And it's probably because of things moving in the soil when I touch it.
Yeah.
There we go. There's another touch.
Second, we administer a soil touch in the same plant. The tool we insert is a metallic scissors, and being that the soil is moist with free ions, we typically get slow and small depolarizations as the scissors are inserted and pulled out of the soil.
I guess soil touch, right?
Yep.
And with the metal electrode, it might give us something. I don't know. Okay, 1, 2, 3. Soil touch. Oh, I did see a little glitch in the recording up there. I'll do it again a little deeper. Soil touch. Yep, it makes a little movement. I'll get it on this camera too.
This is another test that helps ensure our setup is recording properly. Third, we snip a leaf on the same plant we are measuring in. If all the equipment is functioning properly, we will undoubtedly see a large spike in the voltage potential, upwards of 20 to 50 millivolts, after magnification and gain are considered.
So now we're going to cut a leaf, right?
Yep.
Okay, here we go. Let me make sure I keep it on the computer. Ready? Get set. Go. Woo! We got something. Okay. There's the, oh, you can't see it. I can see it. There's your... Alright, and let me get the top so we can see how much we cut. There's how much we cut. And that's about, that was one width of the, that was just about half of the scissor width.
These three tests help us ensure that our connections are good, our noise is minimal, the plant is healthy and responsive, and that all recording equipment is functioning as it should. We then perform these same 3 stimuli on the opposite plant, or the plant not being recorded in. We first perform a leaf nudge, then a soil touch, and finally a leaf snip. The setup has been designed to isolate any conductive connection between the 2 islands of agar, and furthermore to support the mycelium growth and bridging near the center of the agar plate. The 2 halves of the plate are separated with small wooden shims placed on the edges. Then the whole plate is tensioned together with a rubber band stretched around the outside of the plate. This creates a gap between the 2 agar islands, and therefore a break in the electrical pathway. Done properly, the only way a signal can pass from one side of the plate to the other is if a conducting material bridges this gap. That is where the mycelium come into play. The agar acts as a growth medium for this mycelium. Given ideal growth conditions, the mycelium will not only grow on the agar islands, but will actually grow across the gap to the other side of the island, and voila, we have our bridge. Now you might be thinking, could an electrical signal somehow travel on or through the plastic and give a false reading? The short answer is not likely. We have tested the plastic plate by itself, and it will not conduct a signal from one side to the other. Plastic is not a conductive material. However, if the plastic plate had a fine layer of water vapor spread across the surface, it could potentially conduct a signal. This is why we cut the plate in half and completely separate the 2 sides as a control against this possibility. The only thing connecting one plate to another, other than the mycelium, are the wooden shims on the edges and the rubber band on the exterior. We know the rubber band is a very poor conductor, but what about the wooden shims? Could these conduct a signal? Well, we have tested the setup described as is, but with no mycelium inoculated, and we could not get an electric signal to travel from one island of agar to another. This makes sense. The agar islands are electrically isolated from one another, and the shims are in no way touching the agar. This helps support the idea that our data is not the result of signals traveling across the wooden shims. Now that we've talked about the protocol for testing this setup and the methods we use to control for electrical conductivity and isolation, we want to talk about what we would like to see when testing the setup. On the same side, when we nudge the leaf, we'd like to see little or no response at all. When we do a soil touch on the same side, we might like to see a small depolarization. This helps us ensure that our setup is recording something. And when we do a leaf snip, we would like to see a large, rapid depolarization. This would mean that our setup is measuring at least in the same plant properly. When we switch to the opposite side, and the plant we're not measuring in, we would like to see no response with a leaf nudge. This would ensure us that small vibrations in the plant aren't the reason we're getting a signal. When we do a soil touch, it's okay if we see a small depolarization, as this could be expected, albeit that signal would be very weak. Lastly, what we hope to see would be a small depolarization when we snip the leaf on the opposite side. This would mean that the signal somehow traveled from where the leaf was snipped, down the axis of the plant through the stem, across both islands of agar, bridging the gap, and into the other plant that we're measuring in. This would support the hypothesis that an electrical signal from one plant could reach another plant via a mycelial pathway.
Okay, so now we're going to cut a leaf, right?
Yep.
On the opposite plant that we're recording from. Ready? And I will cut a nice snip off right off this thing. Ready, get set, go. Oh, a little artifact. But I wonder if that's movement. Let me cut again. I'll cut up higher this time on that thing. Yep. A bigger change. But I wonder about movement.
What'd you say?
I wonder about movement. I'm just, if you move the leaf, it's not a fast depolarization. It's more like the artifact. Maybe I cut a little nip up here because I don't move the thing. Well, it gave another little bump.
Maybe just try nudging it with the scissors just to see if it gives the same type of artifact.
Yes, I'm going to touch the same leaf I just cut there. No, it doesn't give the same. And I'm touching it pretty hard, the same amount that I would cut it. and it doesn't give the same kind of artifact. So that's pretty cool. And let's go to a different leaf. Let's go to this leaf. Oh, we want to break the mycelium though too.
Yep.
Let's just nip this one. Nip. Yeah, I still see a little artifact. So that's the last nip. That was right there. And you got it on the camera. So that was at 5:45 about.
Finally, if we observe what appears to be a successful signal transmission, the last step is to cut the mycelial bridge with a scalpel and attempt to induce the response one last time by snipping a leaf on the opposite plant. If we snip the leaf and still get the signal, we cannot support the hypothesis that the mycelium conducted the signal. If we cut the mycelial bridge and no longer get a signal, it helps support the hypothesis that the mycelium were responsible for the signal conduction.
And it's separated.
You cut the bridge?
Yes.
Okay.
Okay, so now, plant on the other side. We'll cut this leaf way up here we haven't cut yet. Over here. Let me get a good shot on this. Camera's not in focus. Okay, ready, get set, go. There's a good cut. I don't have anything on the computer screen.
Okay.
And that was a good cut. We can... Let's cut this little branch off of this thing and see what happens.
Okay.
Ready, get set. And I'm moving the bush a little bit doing that. There, just nipped it.
After this final measurement, we perform one last test. We go back to the same plant we are measuring in and snip a leaf. If we see a large and rapid depolarization, this will help show us that our plant was effectively recording electric activity over the course of the experiment.
Now we're going to cut the same plant that we have the recording electrode in just to make sure we're still getting something, okay? Let me find a new spot for it. I'll cut, this leaf's a little yellow over there, so I'll cut up here instead. Ready, get set, go. Oh yeah, big artifact. Okay, so that's good.
Now, we've had experiments that have gone exceptionally well, and we've had experiments that have completely failed. There's a lot of variables moving in this. You have to grow plants, you have to grow mycelial bridges, and everything has to be timed just right. You can't let anything dry out, you can't let anything get too wet. That being said, I think there's still a lot of work to do, but we've accomplished a great deal so far. I believe we found what we're looking for, but we need more data to prove this. I hope this work adds a stone to the bridge of a blossoming new scientific discipline. If you have any questions, comments, or concerns, feel free to leave those below in the comment section. We will be releasing other videos regarding this topic in the future, so if you have found this video interesting, please subscribe so you know when a new video is published. Lastly, I would like to give a big thanks to Dr. Robin Cooper in the Department of Biology at the University of Kentucky. Robin has not only provided the lab space and equipment to conduct these experiments, but has also offered valuable guidance, recommendations, and keeps my spirits high when things don't go according to plan. Thanks, Robin, for always being willing to listen to my crazy ideas and give them a try. I would also like to give a big thanks to Dr. Ashley Seifert in the Department of Biology at the University of Kentucky. Ashley was gracious enough to let me work in his lab while I was studying at UK. He has offered invaluable guidance and criticism on the direction of this project as well as how I should present the work. Thanks, Ashley, for always being open to my ideas and the spirit of cross-discipline collaboration, and for giving me the time of day. And as always, thanks again for watching, and we'll see you next time, friends.